Hello and welcome. Because every function is a process that converts a collection of inputs to a corresponding collection of outputs, a natural question is, for a particular function, can we change perspective and think of the original function's outputs as the inputs for a reverse process? If we phrase this question algebraically, it's analogous to asking, given an equation that defines y as a function of x, is it possible to find a corresponding equation where x is a function of y? So suppose you're walking at an average rate of 3 miles per hour. Your distance traveled d in miles is given by d equals f of t equals 3t, where t is time in hours. Then the function f is distance as a function of time, meaning that function f converts times to distances. And if d equals 3t, then solving for t results in t equals d divided by 3. And we can use a new function, let's say g, to say that t equals g of d equals d divided by 3. Then the function g is time as a function of distance, meaning that function g converts distances to times. Notice that since f converts times to distances and function g converts distances to times, the function f reverses the function g, and the function g reverses function f. Similar work is sometimes possible with other functions, and when we can find a new function that reverses the process of the original function, we say that the original function has an inverse function. Let's look more closely at how functions f and g reverse each other's processes. So again, your distance traveled d in miles is given by d equals f of t equals 3t, where t is time in hours, and the time t in hours to travel d miles is given by t equals g of d, which equals d divided by 3. We know that function f converts times to distances, and function g converts distances to times. If we compose f of g of d, we start with the input of function g, which is distance. And when we apply function g, the resulting output is a time. And then when we apply the function f to the resulting time, we arrive back at the distance we started with. Thus, we can conclude that the composition of f of g of d equals d. Similarly, we consider the composition g of f of t. This time we start with the input of function f, which is time. And when we apply function f, the resulting output is a distance. When we apply function g to the resulting distance, we arrive back at the time we started with. Thus, we can conclude that the composition g of f of t equals t. And these observations lead us to the formal definition of an inverse function. Let f be the function that takes set A and pairs it to corresponding values in set B. If there exists a function g such that g takes inputs from B and pairs them with corresponding outputs in A, such that g of f of A equals A and f of g of B equals B, for each A in set A and each B in set B, then we say that f has an inverse function and that the function g is the inverse of f. It's important to note what the equation g of f of A equals A is really saying. For any input A in the domain of f, the function g will reverse the process of f, which converts A to f of A, because g converts f of A back to A. When a given function f has a corresponding inverse function g, we usually rename g as f inverse. the equation g of f of a equals a now reads f inverse of f of a equals a, which we interpret as saying f inverse converts f of a back to a. Similarly, f of g of b equals b now reads f of f inverse of b equals b. When a given function has an inverse function, it allows us to express the same relationship from two different points of view. For example, we've already shown that d equals f of t equals 3t, and then t equals f inverse of d equals d divided by 3. Observe that both equations are equivalent forms of the same equation. So they really say the same thing from two different perspectives. The first version of the equation is solved for d, distance, in terms of t time, while the second version of the equation is solved for t time in terms of d, distance. This important principle that inverse functions say the same thing from two different perspectives holds in general whenever a function has an inverse function. Let's look at one more property of inverse functions. Suppose we want to find your distance after walking for 2 miles, for 2 hours. Then we would compute d equals f of 2 and see that f of 2 equals 6, meaning you traveled 6 miles after walking for 2 hours. The fact that f of 2 equals 6 also implies that the point 2, 6 lies on the graph of f. So now suppose we want to find the time it takes for you to walk 6 miles. Then we would use the inverse function and compute t equals f inverse of 6 and see that f inverse of 6 equals 2, meaning it takes you 2 hours to walk 6 miles. The fact that f inverse of 6 equals 2 also implies that the point 6, 2 lies on the graph of f inverse. This leads us to the following property of inverse functions. If a point xy lies on the graph of f, then y equals f of x, and using what we know about inverses, that also would mean that x equals f inverse of y, which would imply that the point y, x lies on the graph of f inverse.